So today we're going to start with a linear model. So what we are going to do today, we're going to look at the linear representation. How does it look like in a graph, in an equation, and in a table of values? And then how can we, when we have points, how can we make that regression line? How can we add things together to make that regression line? So when we're looking at mathematical models, right, we have different ways that we can look at things. You can only use So tables, graphs, and equations are all examples of.
I never got to the Excel.
Can we get to that in a bit when we need it?
Okay.
You guys don't need to use Excel right now. You just have to pay attention to me. Okay? So table, graphs, and equations are all examples of mathematical models, right? You either see it as a graph, you either see it in a table, or you either see it as an equation, right? So they're all examples of mathematical. So can you give me an example of a linear model? A graph, how would it look like? A straight line. But in real life, how would it, what would be an example of a straight line? A road, so that's an example of a graph with a straight line. But if you're talking about application, so let's say, for example, the price you're gonna pay for how many pounds of apple you're gonna buy, right? That's a linear function. Because if you're gonna get 1 pound, you're gonna pay whatever 50 cents. If you're gonna get 2 pounds, you're gonna pay $1. 3 pounds, you're gonna pay $1.50, right? So these are examples of linear function, right? Or let's say your wage, if you're getting paid hourly. If you work for 1 hour, that's $14. 2 hours, that's $28. So that's another example of linear relation. Okay? So it represents quantities that increase or decrease by, so a linear relation has to be increasing and decreasing by a constant amount. Over a period of time, or equal. And we said that the graph is a straight line. Do you remember how the equation would look like? Y equals mx plus b. Where is the slope and blank is the vertical intercept. So which one is the slope? M is the slope. And what's the vertical intercept or the y-intercept? B. Okay, so the equation is gonna look like this. You're gonna have a number multiplied by x plus another number. And m is the slope, so that's the steepness of the line, and then b is the y-intercept. Now, the rate of change is constant or not constant for a linear function? Constant, because that's the same thing as the slope, right? Now, what do you do in order to figure out if it's from a table of value? How would you figure out if it's linear or not?
y2 minus y.
So, which is the first difference, right? Which is also can be explained as an equation. So if I do the first difference, and I do y2 minus y1, so I'm going to get -5, I'm going to get -15, and then I'm going to get -25. one linear?
Nope.
No. How about the second one? If I do 40 take away 0, that's gonna be 40. 80 take away 40, so that's 40. And then 120 take away 80, that's also 40. So what can you tell me about the second one? Constant, that means it is linear. Because, you have to be very specific, because first difference is constant. Look at the example below, we have graphs. What can you tell me about the first graph? Is it a graph function or not? And if it is, how do you? It's linear because it's a straight line. So and the second one? It's not linear, right? It could be exponential or it could be half of the parabola. So we can't say, but we can say that it is not linear. Because it's not straight. How about, so we've seen so far the table of values and we've seen a graph. Now we're gonna look at equations. What can you tell me about the first equation? Y equals 2x plus 5. Is that linear or not linear? Linear, it's a degree 1, right? It looks like y equals mx plus b. So it's linear, degree 1. Looks like y equals mx plus b. How about the second one? Not linear.
Why is it degree 1?
Can someone explain why it's degree 1? It doesn't have an exponent, it's a 1. Second one is going to be quadratic, so it's not linear. And how do you know that? Degree 2. That should be a D, not a G. Okay, so what we did here is that we used the 3 different formats, right? Graphs, tables, or equations to see if it is linear or not linear. Do you guys understand that? All right. Can I move to the next one? in real-world graphs of linear relations, the vertical intercept represents the, so when I talk about vertical intercept, I'm talking about the y-intercept. Okay, so if I have a line, this is going to be your vertical intercept, or otherwise it's called y-intercept. Okay? What does your vertical intercept represent in real life situations? What do we call it? It is your dependent, but y is always your dependent. It doesn't have to be the y-intercept only. The y is always your dependent. The y is always, doesn't have to be only the y-intercept. The y-intercept is your initial value, right? So what happened, what was your y value when you started initially? Okay, so the vertical intercept represents the initial value of the dependent variable. And the slope represents the rate of change. Okay, so you need to know both of them. You need to know your initial value, you need to know the rate of change in order for you to be able to graph or to be able to solve any questions like that. Okay, are you guys okay with this so far? So far we're just doing a review, okay? Nothing new. Okay, I want to read this question, and I want you to think about how can you compare these two equations, what's similar, what's different, and just we're going to discuss it in a few seconds. So, explain what the numbers in the equation represent and how do the two equations compare to each other.
0.5 is the rate of change.
0.5 is the rate of change in the first equation. How about in the second equation? What would be the rate of change?
T.
What's in front of t? What's the coefficient of t?
1.
1. So the rate of change is 1. Okay? Yes, it's invisible. It's not there, but it's 1. Right? So right here, you should have a value of 1, but they don't have to write it, right? You don't have to write it. Okay, so the rate of change for the first equation is 0.5. What does it mean with respect to this problem? What does t represent again? T is,
Seconds.
so it's time in seconds, right? So for every degree that you change, degree Celsius that you change, how many seconds do you need? 0.5 for the first one. It's 0.5. Sorry, for every 0.5. Remember that this means rise over run, right? So this is rise over run, right? So the rise in this case, let me just write it like this. So what's happening here is on the y-axis, you have the degree Celsius, right? On the x-axis, you have time in seconds, right? So for every 0.5 degree increase, you need 1 second. That's what this means, because this is rise over run. Okay? So for this one, for every 0.5 degree increase, that's your rise, you need 1 second. Does that make sense? We're talking about coffee, right? Putting it in a microwave. How about this one? What does it mean? For every
1 degree.
1 degree increase, how many seconds do you need?
1.
1 second. So which one is better?
1,000.
This one, right? Because you need less time to heat it to the same temperature, right? Because you're going up by a degree every second. The other one, you need 2 seconds to go up by 1 degree, right? So you need twice the amount of time to heat it to the same temperature. Make sense?
Can you just go over that again? So why do you say it's better? Because you have to.
Because this one, for every 1 degree, you only need 1 second per 1 degree, right? For this one, you need 2 seconds per 1 degree, right? In order for you to go up 1 degree, you need twice the amount of time. Make sense?
So how do you do this? It's like 0.5 by, how do you do?
This is over 1. Any number that doesn't have a denominator is over 1, right? So the slope is rise over run, right? So if you're looking at rise over run, you're going up in degrees over in seconds. Okay? How about the 20? What does the 20 represent? The initial temperature of the coffee, right? So it's the initial temperature of the coffee, which was 20 degrees for both of them. Both of these are linear functions, right? Because they look like y equals mx plus b. They have degree 1, right? Both of them. Okay. Are you guys okay with this? Comparing the two?
So what's the last sentence? Initial, is it temperature?
Temperature, yeah. Of coffee is 20 degrees Celsius.
Is that is or in?
Is. Okay. So now you need to open Excel. Go to the bottom left corner. Just, and then type Excel. Just type Excel. Okay. Start typing Excel. Yes.
Sorry.
So, mine is locked out now.
Log back in. Okay, so when we go and collect data, right, no matter what the data are that we're collecting, most of the time we're gonna get data that they're not gonna fit perfectly, right? They're not gonna just give us a straight line or a straight or a parabola or whatever, right? So what we do is we actually take this data. You always have to have two variables. You have dependent and independent variable, and then you plug them into Excel, right? When you plug them into Excel, you can graph what we call a scattered plot. And then after you graph your scattered plot, you can do a regression graph in order to see which one fits better, which type of graph fits better. Is it linear? Is it a quadratic or is it an exponential? There's other types, but this is what we focus on here. Okay? So what we need to do, we need to know how to plug in, how to put these information in Excel, and how to graph it, and how to find the equation. Okay? So the first one we're going to look at is called the linear regression. So we can use linear regression to model data that appear to be linearly related. So how do you know if the linear regression is a good regression line? You're going to have to look at your at how well does that line of best fit actually line up with your points. Okay, so if it fits perfectly, that's great. If it fits like semi-perfectly, that's also good. We also look at what we call the R-squared value. I'll show you how to find it, and then that closer to 1, the better it is. Okay, so we'll talk about this while we graph. So right now what we're going to do is we're going to open Excel, and then we're going to graph. What we're going to do, we're going to graph the equation.
Come on, Alex. Do you know how to make it use these numbers?
There's something called I don't see it there. I don't know how to do it.
Eric. What's the number lock on the album? What's the number lock on the album? Yeah, trying to use the numbers over here. Contra.
Can you please open for him? Thank you. Just going out. I don't know which one would be the num lock.
Thank you.
All right. So this is what we're gonna do. We have the year and the age. Which one should go on the x-axis? Which one should go on the y-axis? Which one should go on the x? The year or the age?
Year.
The year, right? Because that's your independent. So so you're gonna enter the year, so 1975, in the A value, and then we're gonna enter them going down. Come on, I think it's F17.
When you have years, is it usually on the x-axis or it depends?
Usually it's on the x-axis. Thank you for locking this up for me. What did I press now? I think it's this. I don't know what I pressed to lock this so I can remember. So enter the years, please, in the first column. And in the other column, you're going to enter the age, 27.4. So this is shows the median age of Canada's population from 1975 to 2000.
What was you getting the typewritten? What did you get in the typewritten?
No, that's just the, that's just those numbers.
What? You can't use this? You can't use this one?
No.
No, I mean, well, mine doesn't work, so.
So we all entered it?
No, not yet.
During this class?
Just during this class.
Yeah.
I don't think I'm gonna be doing anything on this. I don't think we can get it back on this. I wanna talk to you about this. I'm just worried that I'm gonna miss the class. I really can't be wasting my time. I don't wanna be around. I'm gonna here every day to the end of the class. And I'm just worried, obviously, for good reason. So like, I don't